Hi there, my name is Kunal Marwaha. I'm a graduate student at U Chicago, and I'm presenting some joint work with Boaz Barak from last June, algorithmic limitations for maximum cut on high-girth graphs. So I'll give a brief overview of the problem that we're looking at, and I'll talk about the state of the art for max cut on random graphs, and then I'll give an overview of the main technique, which is why we're presenting at this conference. So what is maximum cut? You take a graph, you split it into two parts, and you're trying to maximize the number of edges between partitions. In the exact case, this problem is NP-hard. So most algorithms people look at are approximation algorithms. There's a notable algorithm, the Gomez-Williamson semi-definite relaxation. This is a classical algorithm, and it's optimal only in the following sense. It's optimal if the unique games conjecture is true, if in its approximation ratio. What that means is that the approximation ratio is the number of edges that you can cut over the optimal number of edges. And it's shown in the worst case that you can cut around 87% of the edges. However, I'm actually interested in a different kind of metric. The metric I'm looking at is cut fraction. This is just cut as many edges as possible. And I'll be looking at mostly random graphs. So in random graphs, the maximum cut as n and the degree grow large is half plus just a smidge, half plus some constant over square root d, where d is the degree. So 87% of that is going to be below a half. So I'm interested in algorithms that perform well in cut fraction, not necessarily in approximation ratio. Also, the semi-definite program is not local. And so what does local mean? Let's call an algorithm k-local with respect to some graph. If you first label every vertex, IID, from some distribution, and then you recompute every vertex's label using only the radius k neighborhood of the graph. And the key idea here is that local algorithms at small k can't see the whole graph. It's a restricted model of computation. And so the question here is, can local algorithms perform well on these problems? They should be limited in some capacity. Also, local algorithms aren't just limited to classical algorithms. I'm also interested in quantum computation. And the state of quantum computers at this time is that we have these NISQ machines, or kind of noisy machines, where you can run a few algorithms, but you can't run very much. Every operation, which is like a two-wire operation, contributes some noise to the system. And so you can only do so many of these before the noise overwhelms the signal. And so we're modeling this kind of computation with local quantum algorithms. And in fact, for combinatorial optimization, the most popular quantum algorithm to run in the near term is the QA-OA, which is an example of a local quantum algorithm. But the point here is that with these noisy machines, you can't have a very high circuit depth. And so your computation is restricted. And so the big question, the overarching question here is, are these near-term machines useful for combinatorial optimization compared to regular computers? A graphic that might sum up some of this is you have these Q-local machines, and Q-local at depth 1 is this green line. Q-local at some constant depth is the yellow line. And the classical algorithms are the black line. And the question is, does the green or the yellow line, cross the black line? And if there's some crossing, then there is some, CSP where you can solve it better on a local quantum, using a local quantum algorithm, which you could theoretically use a quantum computer in this decade to solve. But we're not even sure if this happens. So we've named this NISQ optimization advantage. We're not sure if this is possible. There's no theory to support it yet. And we have a couple of results maybe suggesting it might not be possible. There's this blue line I've written here too, the scalable fault-tolerant quantum computers. So the quantum computers of the long term, after you have error correction and low noise and millions of qubits, what can you do? And you can do anything a classical computer does. And you might actually be able to do more. But again, we're not sure about any of that, and it won't be relevant for many years. So what's the state of the art for maximum cut? So here I have a line plot, and the line plot is cutting on random graphs. In a random graph, again, you have half plus some constant over square root d. That's the cut fraction, or the percent of edges that you can actually cut on a random graph. And so through a really fascinating connection to spin glass theory, the Parisi value, 0.76 something, is the optimum you can do on a random graph as n and d grow large. And so that 0.76 on the right side is kind of your target. Now, when the QAOA was analyzed at its lowest depth, this QAOA is the popular quantum algorithm that is also local. And at the lowest depth, they got to 0.31. And it's close to 0.31. It's like 1 over 2 square root e or something. But the point is that it was actually the best known algorithm, at least measured on this metric. And so a big question was, wait, is the QAOA really successful on this problem? And it turns out in 2019, the answer is no. And there was a reanalysis of a threshold algorithm that was classical, and again local. And it showed that this one local algorithm also gets about 0.33, which is a little better than the QAOA. But the point is the QAOA is not, special here. And of course, this is just at the lowest depth. What about a higher depth? So I did some work last year that said, no, it's actually not true at 2 either. The QAOA does better, but so does this threshold algorithm. And so a question here is like, how well does a quantum algorithm do, but also how well do classical algorithms do? And so we have 2 results in this document. The first result is that all one local algorithms are bounded away from optimal. And so this is using a really cool new technique of random walks of correlations. This shows that any one local algorithm, quantum or classical, cannot achieve higher than this 0.71 value. So it's a non-trivial result. It's kind of weak, and there's probably lots of ways it could be extended. But it does show a block, like a maximum that you can achieve using a one local algorithm. We also have a result that I won't talk about in this talk that is a polytime classical algorithm that gets to 0.63. And this is a restatement of some earlier ideas on Gaussian waves, and it's has some relationship to the semi-definite programming algorithm. But it's actually outdated. It's not super important anymore because as of November, Andrea Montanari and collaborators found a classical algorithm that's asymptotically optimal. So there is a gap between these one local algorithms, quantum or classical, and the classical algorithm. So there is a classical algorithm that gets optimal, at least asymptotically. And this shows that at least for max cut on random graphs, that yellow line in that figure will never cross the black line. Okay, so I'll give a brief overview of the main technique, which I think is pretty cool. So the theorem we have is that when the girth of a graph is at least 6, a one local algorithm can output a cut of expected value half plus c over square root d, where c is less than some value, and it's 1 over square root 2, about 0.71. Okay, so how do we get this? So I mentioned before that I'm using correlations of random walks. So if you have a random walk on a graph, after you walk, let's say, s steps, you're going to be some distance away from the origin, and that distance, it's probabilistic, and you can get there, you can calculate the chance of being distance d from the origin. So if you're distance 1 away from the origin, the correlation of labels that are adjacent is actually related to the chance of being cut. Because if your labels are different, then you'll be in different partitions, and the edge will be cut. If your labels are the same, you'll be in the same partition, and so you won't be cut. So the distance 1 correlation is actually it has a really simple connection to the cut fraction. And if you have a correlation at some distance that's large, over 2k, for a k-local algorithm, then you'll be outside of the light cone, so to speak, of this k-local algorithm. And so there can't be any correlation by the definition of a local algorithm. And this definition of local algorithm has really nothing to do with classical or quantum, just the idea of locality. And so any results we prove using these methods are going to be true for quantum and for classical algorithms. So first we relate like, we're going to look at one local algorithms. And so 3-step walks, let's look at a 3-step random walk. If you walk 3 random steps, you're either going to be distance 1 or distance 3 away. And if you're distance 1 away, it's like you took a 1-step random walk. But if you're distance 3 away, there's no correlation. For at least for one local algorithm, you're outside of the light cone. And so you can relate the chance of correlation from a 3-step random walk to the chance of correlation from a 1-step random walk. Because in both examples, there's only one contribution from distance 1 away. So this is kind of like the key point here, that you can relate both, walks that travel too far and you have 0 correlation, and walks that travel really close, and distance 1 means that's the kind of the thing we're looking for. So from here we use Cauchy-Schwarz, and we can say that when you random walk, let's say 4 times, it's as if you apply the adjacency matrix 4 times. Because you're randomly going to a neighbor, which does involve backtracking. And so because in this form you can use a Cauchy-Schwarz to say the chance of walking 4 steps is going to be at least as big as the correlation at 4 steps is going to be at least as big as walking 2 steps squared, or walking 1 step to the 4th. And you can use this inequality to relate 2-step to 4-step random walks to 1-step random walks. And so putting all this together, you're able to bound the expected correlation of a 1-step random walk, which is just a distance 1, that's just looking at neighbors, which the cut fraction is exactly related to this value. This 2 over square root d becomes, the c becomes 1 over square root 2. So hopefully this was an overview of how you can use correlations of random walks to bound things about local algorithms. Because when you're very close, that's the value you're seeking, and when you're very far, the correlation's 0. Unfortunately, we weren't able to generalize this to higher locality with, and still get non-trivial bounds. But it's possible that related problems, we can use this technique and still find out something new about local algorithms. Okay, so what's next? So on max cut, the overarching question that at least I've been after is, do classical algorithms outperform all quantum local algorithms? And for max cut on random graphs, asymptotically, the answer is yes by the Montanari paper. But we don't know, let's say, on graphs of large but finite girth, or let's say a constant depth local algorithm that's classical versus a constant depth quantum algorithm that's local also. And we also, there's kind of a bigger question here, is quantum computing useful for combinatorial optimization? And I think there's some real theoretical doubts that there's no valid, there's no proven area that shows that quantum computing, even in its fault-tolerant way, is better for combinatorial optimization than classical computing. And so not only is this may not be useful in the near term, this may not be of a great direction for quantum computers to look at. And so if we're spending a lot of money thinking about quantum computing for optimization, maybe it's best to put that money somewhere else. So with that, thanks. I'm at U Chicago now, and you can visit my website. One other thing I wanted to mention is we put a summary of this work on the archive wiki, which is like a place you can put summaries and notes of the papers you read. You can explore by topic. You can look at a bunch of papers about the QAOA. I'm looking for contributors. I started the site last year. Feel free to email me about it. And thanks.